This is for Mr. Sweeney's AP Physics C class. Today we're going to be talking about inclined planes, which is section 4.8 in our forces notes. And an inclined plane is a surface that makes an angle with the horizon. So it's any ramp, hill, something of that scenario. And when we talk about inclines, typically we focus on the force of gravity, which causes an object both to stay on the surface that's inclined, as well as to try to force the object down the incline. Now the rate at which the incline slides down the surface is dependent on a couple of things. First, the angle the surface makes with the horizon, and the force of friction that acts between the surface and the sliding object, and that depends on the mass of the object. So when you look at the force of gravity that's acting here, there's two things: the mass of the object, which is going to determine its force of friction, and the angle the surface makes with the horizon. If we look at the inclined plane, there's always two forces acting upon it. There has to be the gravitational force pushing down, and this is both pushing into the hill and down the hill. And we also have a normal force pushing out of the hill. This is the reactionary force from whatever is pushing into the hill. So you have force of gravity and normal force. These will be in every problem. There could be more if you introduce any outside forces here. We'll have more forces acting on this. The coordinate system for the inclined plane. Because the inclined plane is either going to have the object move down or up the hill, that'll be parallel to the surface, but it'll always be stuck to the hill perpendicularly. So when we're looking at our coordinate system for an incline, we want to orient them so that they are parallel and perpendicular to the hill. The perpendicular portion of it, the net force is always going to be zero. So whatever forces are pushing into the hill will be matched by a normal force pushing out of the hill, and these have to equal, because otherwise the object would either leave the hill or dig into the hill. Either scenario would not make this an inclined plane problem. So we always have a perpendicular condition that has a zero net force. In the parallel dimension, it's either going to be stationary, where all the upwards and downward forces are equal to each other, or the object could accelerate up or down the hill when the friction of the object is either overcome by an applied force or overcome by the force of gravity pushing it down the hill. Now, one thing that we'll always do is we will always resolve gravity into the parallel and perpendicular components, and this is our starting point for all inclined plane problems. So here I've shown the force of gravity acting on an object on the incline. There's one force that's pushing into the hill. That would be the force perpendicular to the surface, and there's one force parallel to the hill. This would be the force parallel to the surface. The force applied down the incline from gravity will always equal the parallel component of the force of gravity in inclined plane problems. Now remember, when your sine is what makes you slide down the incline, so it's always going to be the sine function for this. The normal force will always be the reactionary force. That's going to be the cosine theta times your force of gravity that's pushing you into the hill, and the normal force will be a responding force. And again, this normal force and the perpendicular component of your gravitational force will always equal out, plus any outside forces will still have equilibrium in the perpendicular direction. So let's try a problem. In this example, a 5 kilogram box rests on an incline which makes an angle of 15 degrees with the horizon. I want to know what are the parallel and perpendicular components of this force of gravity that's acting on this box. So here I have my object on the incline. I want one force which is perpendicular to the incline. This is the cosine theta times the force of gravity being mass times acceleration due to gravity. And then parallel to the inclined surface, we have mg sine theta. So these are our components for that. Looking at the parallel aspect of it, so this is what's trying to make you slide down the hill. We have a 5 kilogram mass times 9.81 meters per second squared. That's our force of gravity multiplied by sine 15, and that gives us a force parallel to the incline of 12.7 newtons. if you're looking at perpendicular to the incline, here we want to use the cosine of it. So that's 5 kilograms times 9.8 meters per second squared times cosine 15. This is the perpendicular component of the force of gravity, and that comes to 47.3 newtons. Note that our perpendicular component is greater than our parallel component, and this makes sense for a shallow hill. If you're looking at an AP style problem, that last one being a honors style problem, here we have a similar scenario, except for gravity is not the only thing acting on this box. We have a horizontal force acting on it. The problem reads that a block of mass m acted upon by a force of magnitude F directed horizontally to the right as shown below slides up an inclined plane that makes an angle theta with the horizontal. The coefficient of sliding friction between this block and the plane is mu. So I ask you to do two things here. The first one being to draw a free body diagram of this. The second is to find an expression that expresses the acceleration of the box as it's moved up the hill. So let's start with our free body diagram. The first thing we're going to want to put on is our two components of the gravitational force. So that's going to be mass times gravity, cosine theta. That's perpendicular. And we have mass times gravity, sine theta, is our parallel force. We have a force acting perpendicularly on this, and acting horizontally to the ground. The perpendicular component of this is going to be the force applied times sine theta, sine being the component that's opposite of the angle. And then we have one that's parallel. This is going to be F cosine theta. So for the two forces that are external, gravity and the applied force, we have these forces acting on the object. Now this doesn't tell the full story, so we still need to consider normal force, which we know is acting on this, as well as frictional force. Now the normal force is acting perpendicular to the surface, so F sine theta and mg cosine theta are pushing into the surface. The normal force is reacting to that, pushing out of the surface. And finally, we have gravitational force. This is frictional force. This is our force of friction. That's our mu times whatever our normal force is. So it will really be mu times summation of F sine theta plus mg cosine theta. And this is our free body diagram. In order to find the vertical, we want to try to find our normal force. I had mentioned that our net force vertically is always in equilibrium, always zero. So our F net will always be pointing downwards, mg cosine theta, also pointing downwards, F sine theta, so those are both negatives. And then pointing upwards is our normal force. Rearranging this a little bit, we can see that our normal force is equal to mg cosine theta plus F sine theta. So these two components, mg cosine theta, F sine theta, represent our normal force. We need to write an expression for our normal force because we'll need it in the horizontal direction or the parallel direction because it's a component of the frictional force. Moving to the horizontal component, we know that the net force in the horizontal direction is going to be non-zero, but it will be the sum of all the forces, and that's equal to mass times acceleration. So bringing that mass times acceleration down, we have a F cosine theta, that's the force pushing it up the hill, that's what's driving it. And then detracting from that, or heading in the leftward downward direction, we have an mg sine theta, so that's the component of gravity pushing down. And we also have a normal force times mu. This is giving us our force of friction. So we have the applied force up the hill, take away from that the gravitational force parallel to the hill, and then you also have to subtract from that the force of friction parallel to the hill. Now we have a function for force normal, so we can take this last term here, force normal, and replace it with what force normal is equal to. And that gives us a very similar F cosine theta minus mg sine theta, but here I have two terms that force normal is equal to, mg cosine theta plus f sine theta, but when you distribute that negative mu, it's negative mu mg cosine theta minus mu f sine theta. Now they asked us for the expression to be solved as acceleration, so we'll divide both sides of this by mass. That leaves us alone acceleration on the left. That's equal to force divided by mass cosine theta minus, the m's cancel out in the second term, g sine theta minus, here we have a mass that has been canceled out. This is ug cosine theta. And then finally, we have a force in the numerator here. That would be mu force divided by mass sine theta. And this is our expression. So acceleration equals f divided by m cosine theta minus g sine theta minus mu g cosine theta minus mu f divided by m sine theta.